Our first plenary talk will be given by Professor Tim Rogers of the University of Bath. Professor Rogers is a full professor in the Department of Mathematical Sciences at the University of Bath, and he is interested in understanding and predicting the behavior of complicated random events and processes, in particular when there are network or spatial structures involved. He has published several peer-reviewed journals, and he will be giving us a very relevant talk today titled Predicting the Speed of Epidemics Spreading on Networks. Professor Rogers, it is a pleasure to have you here today. Take it away.
Hi there. Thanks very much. Thanks for that nice introduction. I recognize it from my website. So I'm gonna talk about a topic that unfortunately is quite topical. It wasn't topical when I started working on it about 5 years ago, but events have overtaken us. So this is about epidemics spreading on networks, and in particular how fast they spread. But it's going to be towards the end of the presentation that I get to talking about speed. To begin with, I'm just going to be talking about who is most likely to to pick up on a contagion that's spreading through a network. So let me share my slides if I can find them. Here we go. Share. Now I don't see them. Sharing is paused. Bring your shared window to the front. This is no good. Why did we practice this if it wasn't going to work, honestly? Right, let me try now. Share screen. Here it is. Share. Hopefully you see this. And now if I put it full screen, you see that.
Perfect.
I'm good. We got there in the end. Okay.
Yeah.
I'm eating up my time. Right, so this is the topic of the talk. Predicting the speed of epidemics spreading on networks. This is me, as you've heard about. And I'm going to start with a picture I've stolen from Wikipedia on the Black Plague. So this is a terrible disease that spread through Europe in the 1300s. And this figure has color-coded regions according to when the disease was first observed. And you can see that there's this sort of banding structure as a wave of contagion propagated across the continent. And we can actually calculate the speed of that propagation, and it was about 1 mile per day. So why was it so small? Well, this was the 1300s. So how did it travel? It traveled basically by foot or by horse. And the kind of trade networks that we have today weren't in place. And so this contagion was limited in the speed of spread across Europe. Now, if we contrast this to what we've experienced recently, here is some data from early on in the COVID-19 outbreak from Johns Hopkins. You see it, as we all know, it began in China. And then in a matter of weeks, started popping up all over the place. And two things here are different. One is that it's incredibly fast. And two is that there's no neat spatial ordering to this. So we had outbreak, if you'll remember, we had this outbreak in Italy coming up second, and then it sort of started popping up all over the place. So that kind of spatial notion of spread was lost, and we have to think about other ways in which we can describe spreading. So what is different in these two models? Well, as I've sort of alluded to, this is something that's changed. So this is a map of the world drawn by overlaying flight paths of aircraft. And you can see the outlines of the major continents, and you can see Europe and North America and so on. So we have a huge and very fast international travel network that just wasn't present in the 1300s. And then secondly, there's social networks. So in the 1300s in Europe, people lived in villages, and they probably only ever interacted with other people from those same villages. And you could go years probably without hardly meeting only a handful of outsiders. Now, or until recently, we all traveled all over the place quite a lot, and had very broad social networks that were very highly overlapped and well mixed. And that creates an environment where a disease can spread extremely quickly. So how fast can an epidemic spread in a network? So I'm going to tackle this with mathematics, and in particular with a model. So I'm going to pose a very simple mathematical model and try and understand its properties. So this isn't about going and gathering real world data and doing a very careful kind of simulation or something. It's more about stripping down to a very simple model and trying to understand how that behaves. Now, this is joint work. Well, so I started on my own 5 years ago, and then I've got 2 subsequent papers, one with Ryan McCoon from King's College, and one with Sam Moore, who was a PhD student of mine. He now is a postdoc in Warwick, and he's actually part of the group that are modeling the vaccine efficiency simulations for if and when we get a COVID-19 vaccine. So he's sort of gone from doing something very theoretical to suddenly being thrust into super duper important applied maths that could save lives, hopefully. Okay, so the model I'm going to use is a network SIR model. And it's a simple model of an epidemic spreading on a network of individuals. So here, these dots are representing people, and the edges are representing possible infectious contact between those people. We're going to take the number of people to be fixed and in fact the network to be fixed as the disease progresses. And people can fall into one of 3 classes, S, I, and R, standing for susceptible, infective, and recovered. So we start with one infected individual and everybody else susceptible. And the infection can be passed along the edges of the network. And this this transmission doesn't happen instantly. There's some delay period. So after you've been exposed to a disease, it takes some while for it to incubate in your body before you are kind of creating sufficiently large amounts of virus that you might risk passing it on to other people. And then you've got to meet them, and then they've got to develop it. So there's a delay period between one person getting sick and it passing it to another person, even when there's contact. Now, that delay period is highly unpredictable, and so we're going to model it as a random variable, call it x, and it has some density f of x. Now, infected nodes can recover, and we model this by allowing an infinite delay in transmission. So if I receive the disease, but then I recover before I pass it to anybody else, then that's like having an infinite delay between me getting it and passing it on to somebody else. So the recovery dynamic is built into the possibility of not transmitting, and that's by having x allowed to take infinite values. And in terms of the density function, that means that its integral is going to be less than 1. So that's an improper distribution. So maybe another infection takes place, another recovery, and now the disease is stuck because even though there are still susceptible individuals and infected individuals in the network, there isn't a path between them. And so nothing else can happen other than the disease recovering, and then this is the final state. Okay. So a key quantity, if you're interested in whether or not this disease is going to spread, is the possibility of it passing just over one edge. And we're going to call that the transmissibility. And that's the total integral of this F density. So that's the probability that the delay is finite. And this is absolutely crucial for the disease, because if it's too small, then it's sure to die out quickly. So a small t corresponds to the situation where most people recover before they pass the disease on, and then it's unlikely that there's going to be an outbreak. On the other hand, if t is large, if it's close to 1, then every infectious contact, it's almost certain that eventually the disease is going to pass along there. And so a major outbreak is going to happen. So this whole process I've described is a random process, so it's going to play out differently. But I've got a couple of sort of toy examples here that you can think of as I go through these slides for what happens when transmissibility varies. So for large transmissibility, we're going to have very quick infections. There's not much delay. And most people who have an infectious neighbor will be infected themselves quite quickly. So this disease is going to spread through this network very rapidly, and only a handful of nodes are going to escape. On the other hand, if transmissibility is low, then it's slow to progress, and the final size is very much smaller. Now, if I did this again, I didn't really simulate that, right? I just drew pictures, but suppose I'd simulated that. If I simulated another version of it, I would have got a slightly different cluster for the final outbreak. And so for each node, you can say, okay, how likely was that node to be infected at some point in the spread of this disease? So that's the first thing I'd like to try and calculate. So here are some of the questions you might have about this model. So one is, as I mentioned, which nodes are most likely to be infected. What's the critical value of transmissibility for a given network? So how infectious does a disease have to be so that it can survive on this network? And then we get onto these speed questions. So how fast can it spread, and which nodes might be infected first? Are there certain nodes you should watch out for because they're more likely to get it early on? Now, the technique, these are difficult questions, right? And you think this is on some complicated arbitrary kind of graph structure. So we need a technique to try and calculate. And the technique I'm going to use is something called message passing. And it comes from the statistical physics literature and also actual statistics, where it's used as a computational tool. But you can also use it as a way of getting approximations to quantities that on networks that seem very hard to compute just naively. And it's all about thinking, what are the influences between edges on the network, and how can something spread down one edge and then another edge? So in this context, I'm going to model, in this model, I'm going to look at certain special times. So for each node I and j, I'm going to label ti to be the infection time of that node, and infinity is allowed, and that's if that node never gets infected. Then there's ti from j, and that's going to be the time that node j has an infectious contact with node I. So that's node j having been infected and trying to pass it on to node I. And finally, there's this delay time that I've already mentioned. So xi from j is the delay between node j being infected and it attempting to pass it on to node I. And again, infinity is allowed if that particular transmission event doesn't happen. So thinking about the structure of the network allows us to write some equations that relate these random variables, these special times, to each other. And they look like this. So the first one says, okay, when is node I going to be infected? Well, you need to look at every neighbor of that node and ask, when did that neighbor transmit the contagion to that node? So I'm looking for the minimum. It's the first time that one of the neighbors tried to transmit. Okay, so now we have these ti from j's. We'd like to know, when did node j try to transmit to node I? Well, first, node j had to be infected by some other route. So we need to look at all of the other nodes that are neighboring to j so that they could transmit it to j, and then we wait for this delay period. So we look at the minimum of the other infection times and then plus the delay between I and j. Okay, now these are equations involving random variables, and they're sort of kind of complicated in structure, being a minimum and a plus. So it's actually easier to express this in terms of the density functions. So if I let capital F be the probability that node I is infected before time t, so the cumulative density function of this random variable, and then similarly Fij is going to be the CDF for the transmission time j from I. So if we assume independence of events, now this isn't really true, but it's going to turn out to be good enough, so I'm just going to plow ahead with it. So if we assume independence of transmission events, we can actually write a formula for this. So the minimum, so in the previous slide, I was taking the minimum of random variables. And in terms of densities, that means taking the product of the CDF, because if you want the time to be small, you need all of the times to be small. If you want the minimum time to be small, every time has to be small. So that means taking a product if the events are independent. Okay, so that's where this equation comes from. And then we have a slightly more complicated form for the transmission here from j to I, because we've got the minimum, so that gives me this product business, but then I've also got to add on the delay. So when you're doing random variables, if you add two random variables, then you're taking the convolution of their density functions. So I need to integrate over all possible delays up to that time, then the probability that that j had received the infection before then. Okay. So this now is a set of equations that describe a relationship between functions. So the random variables now have gone away, and I'm only interested in these smooth functions and the relationship between them defined on the graph. And these are called the message passing equations. In other contexts, they're also known as cavity method or belief propagation. You might have heard of them. So this is going to be the starting point for the maths that I'm going to do. I'm going to sort of take this as an assumption in some sense, a sort of carefully formulated one, and now I'm going to calculate what can I tell about the behavior of this system of equations. Now, in the first couple of questions I'm interested in, they weren't to do with specific times and speeds. They were just asking, okay, how big does transmissibility have to be? What's the chance of a particular node being infected? So for those kind of questions, I can put my time that I'm interested in, t, if I put that to infinity, that's basically just asking about the end state of this propagation. So if I define Ri to be the riskiness of node I, and that's Fi of infinity, so the probability that it's infected at some finite time, then I can write a simple product formula for the Ri in terms of another variable Ri from j, which is going to be the probability that node j ever attempts to pass the disease to node I. And then for my second equation, I get another formula for those transmission possibilities that are along edges, involving t, the transmissibility, so that's the chance that that x variable was finite, and then this variable here that's telling you whether or not one of the other neighbors of j, so some k, managed to infect node j. So this is a closed system of nonlinear equations defined on the edges of the network, and in principle we can go ahead and try and solve it now. So that gives us a procedure for analyzing the riskiness of nodes in an epidemic. So step number one would be to compute the transmissibility, so that's the probability that a disease manages to propagate along one edge. Then you solve this nonlinear system of equations. And then having solutions to these, you plug them in to the formula telling you what's the chance for a particular node being infected. Now, this is a large system, okay? There's one of these variables for each directed edge in the original network, so twice the number of edges. And it's horrendously nonlinear, and so pretty much your only chance is at solving this is going to be a numerical method most of the time. So it's instructive to think about what kind of method you would use and how it behaves. And in order to do that, I'm going to think about the graph, not the graph between nodes, but the graph that describes the relationships between variables in that nonlinear system. So I'm just going to flick back, apologies. So if I look at this nonlinear system here, and I think, okay, for which pairs j and k, do they show up on the right-hand side of some other variable ij? So we can draw a graph of that relationship. Its nodes are going to be ordered pairs of nodes in the underlying network, and its edges have the form, you get a directed edge from lk to ji when k is j and when l is not I. So what does that mean? So we might try and draw a picture for an example. So imagine this was your underlying, very simple underlying network topology. Now, if I draw this graph on top, it has the following form. It looks like a horrendous mess at first. So every edge, let's look at this edge here, every edge in the underlying graph spawns two nodes in the Hashimoto graph, it's called, for the two different directions that you might walk down it, okay? And then you join these directed nodes up with a directed edge if it's possible to traverse one edge and then the other without doubling back on yourself. And this is relevant to the disease spreading because this is saying exactly when, you know, what other transmission events might have happened before a transmission event involving me. So this network or graph of the relationships between these variables is going to contain all of that information for us. So armed with this, we can go ahead and write a slightly more simple form of the nonlinear system that I'm trying to solve. I'm going to define a map on vectors of length 2e to themselves that basically computes the right-hand side of that formula. And my variables are indexed by edges in this Hashimoto graph. And so solving the message passing equations means finding a fixed point, r equals d of r. Now, luckily for us, this isn't a very badly behaved fixed point. It's actually an extremely well-behaved fixed point, and so iteration will work. And in fact, iterating this function here has a natural analog to something that's happening in the disease. So if we think about taking a d-step iteration of this function, what that's doing is it's sort of like the situation in which, an n-step iteration. You're interested in some focal node, but everybody at a distance n or more starts out infected. And then what you want to know is that infection strong enough to propagate all the way in to reach this individual central node? So that's the nth iteration. And so that buys you a lot of monotonicity properties and so on that tells you that this is a well-behaved system to solve via iteration. And in fact, we can go further than that. We can think about when is that iteration process well behaved, and in particular, what other fixed points might you find? So there is one fixed point, which is 0. Okay, so if I had 0 here for R, then I've got a product of 1s, I've got 1 minus that, so I get 0 again. So 0 is always a fixed point, and that's the fixed point corresponding to there being no disease at all. And so we might ask, okay, if everything's nearly 0 and then there's one tiny defect very, very far away, is that enough to cause a spread of possibility of infection across the whole network? That's really a question about the stability of this system. And that's going to allow us to make predictions about when a disease can spread and when it can't. So doing that kind of solution on a particular network, this is the kind of thing you'll find. So what I've done here is I generated a random network, and then I plugged in various different values of transmissibility, and I solved my nonlinear system. And then for each node, I plotted a gray line showing its risk as a function of transmissibility. And you'll notice a couple of things with this. The first is that there is a special threshold below which the disease can't spread. And then the second thing you might notice is that this is a big, complicated smush here. There's a ranking of risk of nodes, and it's a ranking that doesn't seem to be preserved. So I picked out 2, one in blue and one in green, to show you that they can switch rankings as a function of the transmissibility. So I'd like to understand what features in the network determine this ranking at different points, and how do we figure out this special threshold below which the disease can't spread. Okay. So first, let's do the threshold. So for what value of t is a major outbreak possible? So as I sort of explained or hinted at before, what I'm really asking is when is 0 a stable solution of that, of the iteration r equals d of r? Well, I can go ahead and do a straightforward linear stability analysis here. So I take my function describing the output of d for a particular edge. If I differentiate that with respect to one of the input variables, then I find the following form. And then if I evaluate that at 0, then this product ends up a product of 1, so that goes away. What I'm left with is the matrix. First, I've got t as a number, and then I've got the matrix that describes when is e prime showing up on this right-hand side here for a given e. And that's exactly the adjacency matrix of that funny-looking graph thing that I showed you earlier on. So when does a variable show up on the right-hand side of this formula? Well, that's exactly those variables that are linked to in the Hashimoto graph. And so the Jacobian for my function d at the point 0 is exactly t times the adjacency matrix of the Hashimoto graph. So linear stability analysis of discrete time systems tells you what you care about is, do the eigenvalues of this thing live inside the unit circle? And that allows us to relate the transmissibility to the eigenvalues of the Hashimoto graph. And in fact, we find that the threshold, so when are we going to get a major outbreak? Well, we can only have a major outbreak if t is sufficiently big that the eigenvalues of this are larger than 1, which means that t has to exceed the critical value, which is 1 over the largest eigenvalue of this Hashimoto matrix. Okay, so that's finding this critical value. Now we might look at risk ranking. So to get a handle on the ranking of the risk of the nodes, I'm going to ask, how does this risk vector change when I make a small change in transmissibility? So if I take my formula again, and this time I'm going to differentiate it with respect to the transmissibility of the disease, if I call that derivative v, and you'll see why v is a good choice in a minute. So I call that derivative v, I do the differentiation here, so this is what you get. If I then look near the critical point, so near the critical point, most of the risks are nearly 0. So most of this stuff drops out, and I'm left with an eigenvector equation. So this tells me that the constant of proportionality, so how risk increases when you increase just beyond the transmission threshold, that happens linearly, and the constant of proportionality is exactly the top eigenvector of that same matrix. So this one matrix gives you a lot of information. It tells you where is this point above which an outbreak is possible, and it tells you what is the ranking of the nodes near that point. All because of this kind of linear propagation effect that you know, looking further and further away in the network is like taking higher and higher powers of this Hashimoto matrix, and so only the top eigenvalue and eigenvector contribute anything in the end. So that's down near the transition, but I did say that these rankings had a habit of switching over. So what controls things at the other end? So that's just what I was saying, that it's proportional to the top eigenvector. And this has a name, by the way, and it's called non-backtracking centrality. So centrality is just an idea of how important a node is in a network, and non-backtracking centrality tells you how many non-backtracking walks end at that node, basically. Okay. Looking down the other end, so when R is nearly 1, so risk is nearly is very, very high. So almost every node is very, very likely to get the disease. So there, if I try and do a derivative with respect to t, I'm going to find I have to apply several derivatives with respect to transmissibility before I get down to a constant. And the number that I have to apply is exactly the degree of that node. So in sort of lay terms, it's basically saying when a disease is very, very virulent and spreads really quickly and spreads really well, then every extra friend you have is an extra chance of catching the disease, and your risk is kind of proportional to the number of friends you have. So we've managed to answer these questions. We've figured out that the threshold is down here at 1 over the largest eigenvalue of the Hashimoto matrix. And then near there, the ranking is according to this top eigenvector. And up at this end, the ranking is basically just down to degree. So finally, we get to the part about speed. I want to revisit everything I've done, but now instead of taking little t, the time I'm interested in, to infinity, I'm going to keep it finite and see what happens. So I want to adapt the message passing equations to consider the distance from the infection source. And in this case, the shape of t is going to be important. So I'm going to write down a new family of equations that are the same as I had before, but now they're going to be indexed by another number, n. And n is going to describe the number of steps in the graph that the source of the infection is away from the node or edge that you're interested in. So they have the general form like this, which basically says, okay, how does a node, or how does a transmission event happen at n steps from the source? Well, it has to depend on a transmission event that was closer, okay? You can't get transmission events that are further away because they're not on your path. There's a path from me to the source, and that's how the disease is gonna get to me. So let's now examine this system. To get a handle on how that behaves, we found it was quite helpful just to compute it numerically for a simple graph and see what was going on. And what we found actually is that the shape of this function settles down quite rapidly to a kind of a sigmoidal curve that doesn't seem to change between steps or distances from the source. The shape doesn't change, but it just gets shifted. So there seems to be some constant kind of delay, a typical delay associated with a one-step distance change in the network. And this whole curve gets shifted along by that delay every single time step. So the natural question is, can we compute this delay and can we use it to our advantage to find out some interesting things in the network? Okay, so we want to calculate tau, and we came up with a clever idea, which is basically, so okay, so this is an applied maths conference. What is applied mathematics? Well, a lot of the time it's stuff that's linear or stuff that's one-dimensional, because pretty much anything else is usually too complicated to solve. So if you're faced with some tricky applied maths problem, one of the things to do is to see if you can hammer it flat so that it's one-dimensional, or to see if you can sort of stretch it out somehow so that it becomes linear. Now, we're taking the stretching out to be linear route. So what I'm really doing, I'll flick back a slide, this left-hand tail here has a simple exponential curve to it. So if we appropriately rescale, we can find a linear system down in this tail and hope that the delay is consistent. Okay, so this is what we're going to do. We're going to look at very fast transmissions. So that's that left tail, that's small time, so fast transmission. How do you get a disease quickly? Well, you need one of your neighbors to have got it quickly, and then for them to pass it on to you quickly. So that's the linearity. You only need one neighbor to get it quickly for you to get it quickly. So we're going to find a linear relationship between nodes there. So if I assume that t is very, very small, then these f's are very, very small, and that product turns into a sum, and things are starting to look a bit better. And then I remember from undergraduate that I can unpick a convolution with a Laplace transform. So if I apply a Laplace transform here, then I can turn my convolution integral into a product in the Laplace space, and ta-da, we've got a linear system again. And what's more, this sum is involving the same stuff as before in terms of the Hashimoto matrix, except now it's indexed by functions and we're in frequency space, so you have to be a little bit more careful, but the same sort of general messages and techniques apply. So we've got another linear system involving this non-backtracking matrix. Hooray. So what do we think is going to happen? Sorry, I'll flip back again. So what's going to happen in this? This is like a linear iteration. So I've got something, the nth iterate is some number times a matrix product with the n-1th iterate. So this is a bit like the power method for finding eigenvalues, right? You pick some vector, you apply the matrix to it, and then you apply it again and again and again and again and again, okay? So as that goes on, that's going to find some dominant direction, and it's going to stretch out exponentially in that dominant direction. So what we think is going to happen is that it should converge to something that looks like this. The direction is going to be picked out by the eigenvectors of the Hashimoto matrix, and then there's going to be some eigenvalue, and we're choosing to write it like this. Why are we choosing to write it like this? Well, we know it's going to grow exponentially, so we might as well put it in a natural logarithm basis, right? So it's going to go like something like e to the minus omega s times some n, okay? So expect this kind of growth. Rearrange that and solve, and then look back in real time, and you find the delay. So the delay is the maximum over frequencies of this function that incorporates both the network structure through this TC, the transmissibility threshold, and the actual shape of the transmission time distribution. So if you just want to know if the disease is going to propagate, all that matters is the integral of the delay distribution. If you want to know how fast it's going to propagate, you really need to know its shape. And by shape, I particularly care about the Laplace transform. So you solve this equation, and that gives you the typical delay. So we tried this out on some standard large networks that we downloaded from the internet. And so we ran simulations of epidemics on these networks. We computed their critical thresholds, and we computed the delays. And we found that indeed, this is a very, very neat predictor of the speed of the spread in quite a non-obvious way, right? I wouldn't have thought when I started this project that I was going to get some formula involving maximizing some logarithms of a Laplace transform or something. But it turns out this gives you a very good predictor for how fast a particular disease is going to spread in a particular network. So we've just got time to look at, oh, sorry, and I mentioned the shape is important. So how does this delay change if you change the shape of the delay distribution? So, what kind of a transmission profile is more or less dangerous in the sense of it might cause a fast outbreak? So to test that, or to illustrate it, we took a family of distributions, a Weibel family, and they have a parameter kappa that lets you interpolate between something that's got a heavy tail and a peak at 0, and then something that's very, very sharply peaked around 1, okay? So this is the easier case to think about first. If every delay takes a very consistent amount of time, then the amount of time between the source getting the infection and me getting the infection is exactly the distance, right? So eventually the delay per step is going to converge to 1. So that's what's happening up here. Down here, what is interesting about this profile is that here, most of the transmissions take a very long time, but a handful of them are extremely fast. And you only need the possibility of a fast infection to get a very low overall delay. So if fast infection is possible, then what this is saying is eventually that dominates. So in a very, very large network, it's the fastest transmission times that are determining the overall scale of the spread, which is sort of bad news for us, right? Because if you think that you know, it's no good if you can control most of the disease, even if there's still a sort of a small percentage that are transmitting to a lot of people very quickly, that's going to dominate in the long run. So ploughing on, what can we say about who is going to be infected first? So what that really means is we're looking for a delay time, an offset between some node and some other node. So I know if node I is infected at a certain time, do I expect node J to be infected before or after that, basically? So what that means is we're looking for a special delay that we can plug in here so that the chance of I being infected at some time that scales with the typical delay from the source, how does that compare for J? Is it more or is it bigger or less than 0, basically saying is it late or early? So this involves a bit of work because you have to undo the Laplace transform, and if you remember, that means integrating up a contour in the complex plane that's inside your domain of convergence. So you do this, it takes a bit of time. Taking n to infinity gets you an integral form that is very, very tightly peaked around a special value. So most of the mass of this integral is peaked around a particular spot, and then you can do a saddle point method to say, what's the, how do we expand the total mass of this integral around that point. Anyway, you go ahead and do that analysis, and out pops this formula that relates the delay to 1 over S star. S star is the special frequency that's most relevant to the delay time. And then here's the interesting bit. You've got the difference of the logs of the risk. So way back at the start of the presentation, I was calculating risk. Risk is also a good measure. So that's the chance of a node being infected at all. That also turns out to be a very good indicator of when it will be infected, but only if you take the log. So what does this look like? How can we use this in a real network? So here we've taken a bunch of different large networks. We've run multiple epidemic simulations with randomly placed sources, and we've computed the average time until a certain node gets infected. So each node is a dot, basically. So its x-axis position is the average time until it was infected, and its y-axis position is its non-backtracking centrality in a log scale. And we find this beautiful straight line fit. And then the final thing to point out is that, so non-backtracking centrality, this is purely a local property, right? It depends on the node, its neighbors, but not on the bulk of the network. It doesn't know how big the network is. So log of that also doesn't know how big the network is. And what that means is when you're in a very large network, most of the transmission happens extremely suddenly. So if you watch, if you have a movie of when these transmission events are happening and you play it quickly enough that you can see the beginning and the end of the disease, then the actual transmission will be squeezed into a very, very tiny window right in the middle, basically. So if you need to rescale by a log of n, 1 over log of n. So we can expect things to bobble along and then bump, almost everybody's infected, and then it finishes off. Which again is bad news for us, because if you're down here, it's very hard to tell when is this thing going to happen, and how bad is it going to be when it does happen. Okay, so that's me more or less out of time. I'm just going to summarize the main results. So first, we have the epidemic threshold for a network, and this was related to the largest eigenvalue of this special Hashimoto graph that describes non-backtracking walks. When can you go down one edge and then another without turning around? That tells you how transmissible a disease has to be to even survive in the network. Then I investigated the risk profiles of individual vertices. So near this special value, they're basically proportional to their non-backtracking centrality. Down at the other end, where transmission is nearly certain, it's only degree, how many neighbors it's got that makes any difference. And then we did that whole thing again for looking at speeds. So the typical delay between reaching distance 5 and 6 or reaching distance 50 and 51 as the disease spreads away from a source has this funny formula involving the Laplace transform of the delay time distribution and the log of the largest eigenvalue. And from that, we then found that the expected infection time was actually the log of the non-backtracking centrality. And I just want to end with a word of caution. So I mentioned that this was a project, I started working on things like this, 5 years ago, and then Sam did this for his PhD, and then we had this paper out. The paper doesn't mention COVID. The paper came out in January, and I was immediately getting requests for interviews and stuff for media about our paper, trying to link it to COVID, and I turned all of those down. I was pretty frightened of that, to be honest with you. And the reason is the following. All of this work I've been doing has been looking at making individualized predictions. So, measure a network and we can figure out which nodes are at risk, which ones are going to get it first, all that sort of stuff. And you might question whether that's actually desirable information to have or who should have it, okay? So this is a news story from early on in the outbreak, which I suppose quite a few of you probably would have noticed at the time. So South Korea had a very detailed and very public test and trace process where they released an awful lot of information about people who tested positive for COVID and where they had been, what they'd been doing. So this was a news story linking a bunch of cases to a nightclub. There were other things that there were aspects of people's lives that they would have wanted to keep private that became public because their information was released in this test and trace thing. It made me question a little bit, how desirable is it to be using mathematics to make individualized predictions about people in such a situation as COVID-19? So I'll leave that for you to ponder. I'm very happy to take questions. I can see there are some in the Q&A. What's the format, organisers? Should I open that and start reading them out, or how do you want to do it?
Thank you, Professor Rogers, first of all, for an interesting presentation. I believe we have time for one question live, and perhaps we could tackle the rest through the chat box. So okay, sure. I guess the first question is, could you use stochastic graph theory to approach this problem?
Right, so one of the questions I'm often asked, so everything I presented in this talk has been non-rigorous, really, in the sense that I started from a system of equations that I hope will correspond to the spread of a disease on a particular network. And in fact, the results are good, but the reason I say hope is that that's not a controlled approximation. I can't tell you, it's not like a Taylor series where I know the order of the error. I know that it's wrong and I can't tell you how wrong it is. Now, if you want to take this kind of work and do it more rigorously, one of the ways you can do that is by having some control over the networks that you're interested in. So for instance, by generating random graphs and then asking probabilistic questions about what's the probability that the spread of the disease is going to be very different from this solution. So that would be a setting where you can get a much stricter handle on, what's the error involved in this approximation, how you can control that as a function of the networks themselves.
Thank you very much. Once again, we're running a bit out of time, so perhaps we could tackle the remaining questions through the chat.
Yeah, so do I just replies in the Q&A thing, I guess?
This is great, yes.
Will do. All right, I'll stop sharing now. Thanks, everyone.